Hello, I don't have a good impression today because I wasn't aware I was presenting today until a couple minutes ago. But if you have a suggestion, let me know and I'll work on one and we'll see what happens the next week. Okay. But anyway, this is lecture number 18. I guess I can show you what I think Nick does at the beginning of every lecture. He does this. He goes, welcome, welcome, welcome to CS 161 at the University of California Zoom link. And then he says that really loudly. But I don't know, that only makes sense if you've been to one of his online lectures. Okay. So last time we talked about low-level network attacks. So we're going to start at the lowest layer and then work our way all the way up the network attacks. So at the very lowest layer, before we started, we talked about there are different kinds of attackers. There's the off-path attacker who cannot see or modify or drop packets. There's the on-path attacker who can read things, so they can read packets, but they can't modify packets or delete packets. And then there's the man-in-the-middle attacker who can read packets and modify packets and delete packets. So those are the three classes of attackers in our threat model. And then we started to talk about different protocols. So there was one called ARP or ARP. So that's one where you translate your IP addresses to MAC addresses. I think this should say translate IP addresses, not local IP addresses, but or maybe you should say local IP addresses. Basically, if you're in a local area network and you know somebody's IP address, but you don't know their MAC address, the way you would perform that translation is you just ask anybody or everybody, say, does anyone know who has this IP address? And you just yell that out or broadcast it to the entire local network. And you wait to see whoever has that IP address will send you an answer and tell you, yeah, that's me, I have this IP address, and here's my MAC address. So that's the protocol. It's kind of simple, but it works. The problem is there's an attack, which is if there's an attacker on the network, instead of only the legitimate person answering, the attacker could lie and say, yeah, that's me, I have that IP address, and here's my MAC address. Now that's not true because the attacker doesn't have that IP address, but they could lie and say that they do. And if they lie and their answer comes first, then the victim will have to accept the answer. So if you think about it, the victim is only expecting one person to answer this question, right? If you ask who has this IP address, you're expecting one person to answer. But if multiple people answer, you will accept the first answer because you're not expecting a second answer. So if the attacker's response gets there before the legitimate response, the victim will have to accept the attacker's response because they aren't expecting a second response. So that's like a race condition. The attacker has to race the legitimate answer and get there first. And if the attacker's answer gets there first, then any packet meant for 1.2.3.4 will now go to the attacker's MAC address instead of the legitimate MAC address. And that basically gives the attacker a man-in-the-middle capability because they can modify packets before sending them to their true destination. So there were a couple of defenses on this one. One of them was called switches. So instead of just broadcasting every single request, you can have a switch on the network, and the switch maintains its own large cache of mappings, and you can ask the switch to do the mapping for you or to look up a mapping for you. So that's a little bit better. Or you can rely on higher layers for defenses. And there's one called ARP Watch, which is you monitor the network, and if you see something weird, like 2 answers for one request, that would be a good sign that something weird is going on. So that's ARP. And then DHCP is almost exactly the same, but for a different purpose. So DHCP, the purpose is if you are a brand new client and you're connecting to the network for the very first time, and you have to figure out what your configuration is. So I need to know what is my IP address because I don't have one yet. What's the IP address of the router because I don't know that yet. What's the IP address of the DNS server, which I don't know yet. And we'll talk about DNS tomorrow, I think, or maybe Wednesday. But basically all of these things are things we have to ask someone because we don't know yet. And because we're connecting for the first time, we also don't even know who to ask because we're brand new, we don't know who to ask. So again, the best thing we can do is just yell at anybody and say, hello, does anybody have a configuration for me? And hopefully a server will respond to you with a good configuration you can use. But again, you have the same attack where the attacker could give you a malicious configuration. And usually you accept the first one you get. So if the attacker gets there first, then you have to accept the attacker's malicious configuration. And again, if you accept their malicious configuration, all your packets get sent to the attacker first before the attacker can forward them to their legitimate destination. So again, the attacker becomes a man-in-the-middle attacker. And for DHCP, there aren't really any good defenses because you just don't trust anybody. So there's nothing you can do except just broadcast a request. But there are defenses at higher layers, which we're going to start to see, I think, tomorrow. And then the last low-level attack we saw, or low-level protocol, was WPA. This is for Wi-Fi connections. So Wi-Fi connections, now we know they're wireless connections that happen at layer 1. So it's for wirelessly transmitting information at lower layers. And we want to encrypt those connections so that attackers can read them. And the way we do that is we have to derive some sort of shared secret so that we can encrypt and decrypt communications. We also want to use cryptographic MACs, which, because of MAC addresses and people naming things with bad acronyms, we're going to rename the cryptographic MACs as MIX just for now. So enjoy that. And that way you can verify that messages have been sent correctly and that they haven't been tampered with. So to do this, there was this whole 4-way handshake or 7-way handshake or something, right? So it was 7-way, I think, if you didn't optimize, and then if you did optimize, it was 4-way. But basically that handshake, it was kind of complicated and you took a lot of stuff to derive out other stuff. But the short of it was you enter your Wi-Fi password, you use the Wi-Fi password to derive one key, and then that one key is combined with nonces that are random every time to arrive at a second key. And then this is the key that you use to encrypt messages. So if you think in terms of color coding, you went from the password to like a blue key, and then blue mixes with red, which are the nonces, to get purple. So that's another way to think about WPA. Once you get to this key, you can use this key to encrypt messages. And because there are nonces, everyone gets a different key. Now, there are a couple of problems with this. I guess before that, there is one extra thing, which is there's one more key, which is the group key. So everyone shares a group key for broadcasting messages. But anyway, about this, going back to this key, there are a couple of attacks on this. So you could pretend to be an access point and send your own nonce. And if you're on the network and you have the Wi-Fi password and you can send messages on the network, you can pretend to be an access point yourself and give them a bad nonce. And now you share a key with the attacker, right? Or the attacker shares a key with the victim. You could also record a handshake. So look at the MACs being sent or the MIX being sent, look at the nonces, and after that, you can do an offline brute force attack. So guess a password. Once you have a password guess, use your guess to derive a PSK. Once you have a guessed PSK, combine that with the nonces that you know to get a guessed final key. And then once you have a guess of a final key, check that that final key works with the MACs or the MIX. And if they do work with the MIX, then you have the right password. If they don't work, then your guess was wrong and you have to guess again. But that's all offline, so you don't have to ask the access point to compute all that for you. You can just record a single handshake and do all that offline yourself. And then we also talked about how there's no forward secrecy. So if someone does compromise our key later, they can use our key, or if they compromise our key later and they have recorded our message now, then they can also derive the final keys, because if they record the message now, they have the nonces. And if they compromise later, then they have the password, and they can combine those to create the final key. So there's no forward secrecy. So these are all problems. And then we said the solution was WPA Enterprise, which is a new version of WPA. And this one uses a third party to give us a replacement PSK. So instead of just deriving a PSK from the password every single time now, we're going to ask a third party server that's secure to tell us a replacement PSK every single time. So the client will give a username and a password to the third party server. The third party server will verify the username and password. And if they're correct, it will give a replacement PSK to the client and also to the access point. And now the client and access point use a different PSK every single connection. And we saw how if you use a different PSK per connection, that solves all these problems from before. Okay, so that was a bunch of stuff from last time. Does anyone have questions on them? I guess we should have added a diagram here, but since we didn't. Okay, so that brings us to today. So we talked about all the lower layers yesterday. So today we're going to move our way up and start talking about IP layer, which is layer 3. So last time we talked about layers 1 and 2. Today is 3 and 4. So at layer 3, we have something called BGP, which is all about routing packets, and we'll see that. And then we'll move to layer 4, which has 2 different protocols. So you have to think about TCP, which is used for reliably sending packets, and UDP, which is for non-reliably sending packets. So we'll see both of those. And I guess suddenly there's an announcements post in the mysterious location, but okay. So homework 5 is due today because I think today is Monday. Project 2 design doc draft grades are released or will be released after this lecture, I think, on Gradescope. So we looked through all the drafts that people submitted, and I think there's some feedback in there, but again, it was mostly graded on completion, so I think almost everyone got full credit, so there's nothing too much to worry about. But if you want, you can go through and see if there's any feedback for how you can improve your design. And then the actual final project is due August 3rd, so you have about a week starting today to go through and start coding up the project. And again, there's an optional lab, but we don't worry too much about that. Okay. So back to topics. Today, the first one is Border Gateway Protocol. So there's another acronym for you. Before we talk about this, let's just review what layer 3 is. So layer 3 is Internet Protocol, or IP. And this is what we use to transmit data over the internet. So all of yesterday was about local area networks, or not yesterday, but Thursday. All of last time was about local area networks. So we were only talking about networks that were physically in like a small space. So all the computers in a home or in an apartment building, or all the computers in Berkeley, that's a local network. But today we're going to start talking about global networks. So this is computers all across the world. And Internet Protocol is the protocol that lets us transmit data anywhere in the world that we want. And remember, IP uses something called an IP address. So these are addresses that identify a device anywhere on the internet. So yesterday was MAC addresses, which are for devices in a local network. Today is IP addresses for devices on the global network. Now there are two versions. So the one we'll see in this class is IPv4, which is just 32 bits long. So an IPv4 address. Sometimes you'll see IPv6 addresses these days because I guess the internet got so big that there are not enough IPv4 addresses anymore. So sometimes you see these longer ones that are IPv6, and these are 128 bits. But and sometimes because they're so long, you omit the zeros. So if you see this, it might be helpful to know, oh, this is an IPv6 address. But for this class, we'll always stick with IPv4, I think. Now, these are globally unique from any single perspective, which is kind of a lot of words. I think for today, all you have to think of is that these addresses are unique, period. So there's just one IP address with 35.163.72.93. This identifies one device in the entire world. That's not entirely true because of something called network address translation, or NAT, but I think we'll either cover that later or maybe not at all. But for now, you can just think of IP addresses being globally unique. IP addresses also have one extra bonus functionality that we haven't quite talked about yet. But these numbers, they look quite meaningless to us now, but they actually have a secret second purpose, which is these numbers actually encode a bit of information about where this IP address is. So if you look at these numbers as a computer, they actually tell you a little bit of information about where is this computer. So like what continent is it on? If I want to find this computer, should I go east? Should I go west? Should I go north? Should I go south? So looking at these numbers actually can help routers make decisions for where the packet should go next. So that's a kind of bonus feature in an IP address. And MAC addresses don't have this functionality because they're for local addressing. So they don't tell us information like where should I go to find this machine. Okay, so that's IP. Let's see. So I think we talked about this already, but if I want to route a packet at layer 3, remember, all the computers on the internet are not connected together. So it's not like there's a single wire that connects every computer on Earth or anything like that. Instead, we have lots of different local networks that are connected up. And then between two local networks, I connect them with something called a router. So if I want to go from one local network to another local network, I have to hop across a router. Now, if I want to go from one local network to a local network on the other side of the world, I may have to hop across a lot of different local routers before I can reach the destination. So the terminology for this, you'll see this sometimes, is called a network of networks. So I have a network, which is a local area network, and then I have a big network that's comprised of a bunch of small networks, and that's the internet. So it's a network of networks. And to get to my final destination, the packet has to hop across a bunch of different local networks. So how do I figure out which local network to send my packet to if I want to, hit the final destination? So one way to help figure out where things are is called a subnet. So a subnet is a group of IP addresses that all have a common prefix. So they all start with the same number or numbers. And if you see a subnet in the real world, it's usually written as the prefix followed by the length of the prefix. So here's one, it's 128.32.0.0/16. So that's a lot of numbers, but basically what this is it's saying this is all of the IP addresses that start with 128.32. And we know that it's all of the IP addresses starting with this because this 16 tells us that we're looking at the first 16 bytes of this IP address. So this subnet is all the IP addresses in the world that start with this. And presumably they're all in a certain region or they're all located close to each other or something. Okay, so this one, again, because IPv4 is 32 bits long and it says here that we're looking for a subnet where the first 16 bits are shared, there is potentially up to 2 to the 16 addresses here. So you can do that math yourself. Okay. So those are subnets. I don't think they're too important to memorize or anything, but they are useful for routing packets. So as a quick review again, the way we route packets is, well, if it's in the local network, then we're done because we already have a connection to anyone in the local network. So all we have to do is first verify that we are in the same subnet as the destination IP. That means that, if I'm sending a message to Bob and Bob's destination IP is in the same subnet as my IP, that means that we're in the same local area. So I'm done. I don't have to worry too much about any hopping or anything. All I have to do is figure out Bob's MAC address and then send it directly to Bob. So I either use ARP or contact a switch. That tells me what Bob's MAC address is. And then I can just directly send it to Bob because we're on the same local network. So there's no routing or mapping or hopping of any kind. All I have to do is figure out who on this local network is Bob. Oh, it's you? Okay, here's the message. So local network is very easy. If it's not within the local network, I have to do a bit more work because it's no longer in the same local area. So instead of sending it directly to Bob, now I'm going to send the packet to the gateway. So remember, every local network has a router, and the router is responsible for forwarding packets to everybody else on the internet. So I'll send the packet to the gateway or the router. And now it's the gateway's job to send this packet onwards to the rest of the world to find Bob wherever he is. And now it's no longer your job, but it's the gateway's job to find out where Bob is, or if the gateway cannot figure out where Bob is, at least take the packet closer to Bob. And eventually, if this packet hops across enough routers and enough local networks, hopefully it'll get close enough to Bob that it will find Bob's local network. And then Bob can say, yeah, that's me. And then the router will send the packet locally to Bob. So again, you're just hopping closer and closer and closer until you hit Bob, and then you can send it directly to Bob. Okay. So that's how you route a packet. And again, you're hopping across a bunch of different local networks. So another way you can think of local networks is called an autonomous system, or an AS. So this is just kind of another word for local networks or sets of local networks. Let's see. Okay. So usually the way I think of autonomous systems is kind of like a business running its own set of local networks. So for example, if you've ever been to UC Berkeley, they have two Wi-Fi networks. There's like Cal Visitor for visitors, and then there's like AirBears 2, which is another local network for students. So these two are different local networks, or they're different Wi-Fi networks, but they're kind of controlled by the same person, which is the University of California, Berkeley. I don't know why I suddenly decided to use the full name there, but okay. So the UC Berkeley controls, two different local networks, or maybe more, but they all fall under the same autonomous system because they're controlled by the same operator, is how I think of it. But basically, the internet has lots of different local networks, and they're controlled by lots of different people. And each set of local networks that a person controls, or a company controls, or a university controls, I think of it as an autonomous network. So each of these has a number. It's called the autonomous system number. Okay. Each of them handles routing by itself. So if I have a packet that needs to go within the autonomous system, the routers within the autonomous system will handle that for us. again, every autonomous system can have one local network or multiple local networks. And if I want, because they're all connected up with routers, I can forward a packet from one autonomous system to another autonomous system. So this is kind of the same thing as before, but I guess we're taking a bit of a company or a business view as opposed to just a network view. But the protocol here, if I'm trying to communicate between different local networks or different systems, is called BGP, or Border Gateway Protocol. And basically, this is just a way for us to route a packet closer to the destination until it finally gets there. So this is the thing we were talking about earlier, where if I don't know where the packet is, I can at least get it closer to its final destination. Okay. And then usually we're looking for the shortest path, and we're not looking for loops because looping around is a bit of a waste of time. Okay, so here's an example of an internet, I guess. So we have a lot of different autonomous systems. Some of them are connected, some of them are not. So for example, I can get directly from system 1 to system 4 if I want to, but I can't get directly from autonomous system 1 to system 6 because there's no link between the two. So there's no router that can route packets between those two networks, which is fine because there's kind of a graph structure, so I can generally get from anybody to anyone else. So let's say there's a sender here. This sender is part of autonomous system 1, and it's trying to get this message all the way to the recipient, but the recipient is all the way over here at autonomous system 6. So they're not in the same local area network, so I can't just directly finish the packet and send it to the local recipient. They're on different networks, so I have to hop this packet across the internet until I find autonomous system 2. Now the question is, there's this giant graph, and I don't really know who everyone can contact. So how do I get this packet from autonomous system 1 all the way to autonomous system 6 to the recipient? And how do I do so in like the shortest path? And how do I avoid looping around? That's a very complicated question, and it has a very complicated answer. And if you want to see the full answer, I believe CS168, the networking class, will tell you the full answer. But for this class, we're going to simplify it a bit and just give you a kind of preview or a sneak peek of what the full answer might be. So one way you might be able to route this packet is, first, autonomous system 6 makes an announcement, says, I can talk to this recipient. And then autonomous systems 5 and 4, because they're connected to 6, they see that autonomous system 6 has made this announcement, and they announce that I can actually reach 6. So if you go through me, I will send this message to 6, and then because 6 can reach the recipient, 6 will forward it to the recipient. So anybody connected to 6 makes another announcement here. And you can imagine this keeps going, right? So now, if you're connected to 4 or 5, you make an announcement saying, I'm connected to 4 or 5, right? And because I'm connected to 4 or 5, I can send this packet to 4 or 5, they'll send it to 6, and then 6 will send it to the recipient. So this announcement kind of propagates outward from the recipient until it hits a lot of different autonomous systems. And now, oops, I guess that's it. And now the sender sees that, oh, well, if I'm sending this message to the router on system 1 sees this message, says, I can send this message to 4 to 6 to the recipient. So it says, oh, okay, then I'll do that. So this message will now hop from the sender to the first system, to system 4, to system 6, to the recipient. And I think that's the shortest path, but it kind of depends. So again, BGP is very kind of long and complicated, but if you want kind of a shorter version of how it works, it kind of looks like this. But basically, all you really have to know for this class is BGP is used for sending messages across the internet, many hops across different networks, and eventually we just get close enough that we hit the recipient. I think that's all you have to know for BGP. Any questions while we kind of stare at the beauty of this diagram? Okay, cool. I don't know how obvious it's been, but like just before we started lecture, I spilled a bit of water on my desk, so I've been trying to clean that up kind of discreetly, but I think it's mostly evaporated now. Okay. So we've talked about a protocol. As always, we have to now think about attacks because we are a security class. So one attack here is, or one vulnerability here to notice is that we always trust the announcements that came out of neighboring systems. So if a system announced, yeah, I can reach the recipient through this route, I will just accept that and say, okay, I'll take your word for it. There was no sort of verification or anything. We just trusted anyone who made this announcement. So there are a couple of issues with this. The first one is spoofing. We've already talked about IP spoofing, which is if I send a message and I pretend to be someone else, I'm lying about who this message came from. So I'm pretending that this message came from Alice, even though I'm Mallory. Usually, it's the job of the router or the autonomous system to check spoofing. So if you're an autonomous system and you see a packet where the IP is not correct, so we know that this person has IP address X, but they send a message with IP address Y. Usually the autonomous system should notice this, or the router should notice this and be like, wait a minute, you're lying about your IP. So I'm not going to let you send this packet because you're trying to be malicious. So most systems do this, but there are some systems that don't. And that's why IP spoofing is still a problem on the internet, because not everybody does this check. I think the modern number is something like 75% of people defend against spoofing, and then 25% don't, something like that. But basically, some people don't, and that's a problem. So we have to worry about that. And as we talked about before, yesterday, this allows us to send packets that look like they're coming from someone else. Okay, there's not a great defense against this, because if someone doesn't check spoofing, then they just don't check spoofing. So we will look at higher layer protocols. Again, I think we're kind of punting everything higher, but I promise you eventually we'll see a higher layer protocol that does defend against all of this. So stay tuned. There's another one called BGP hijacking. So in this case, if you have an autonomous system and you're malicious, you can just lie and give an announcement for a network that you can't reach or that you're not responsible for. So you can always lie about all those announcements from the previous slide, and that's called BGP hijacking. So maybe if you're autonomous system 3 and you're malicious, you claim that you're responsible for this subnet, even though you're not. And now anybody who wants to send a message to this subnet could potentially send it to you because you claimed that you can reach the subnet, even if you can't. And that lets you be a man in the middle, because now anybody who wants to send a message to these IP addresses will send it to you. You can now modify this message however you want and then forward it to that legitimate IP address. So now you're a man in the middle if you broadcast that you're responsible for this subnet, even when you're not. So again, kind of similar to what we saw yesterday, which is if you claim something, then people will generally just trust you and send the messages to you, and that lets you be a man in the middle. Again, we're going to kind of keep using this excuse, but there will be a high layer defense against this, so stay tuned. Okay, so those are the attacks on BGP, and I think that's the end of BGP. So does anyone want to ask questions about how it works? Again, we don't go too far in depth for it, so if you do want to see the full BGP in all its glory, 168 is the place to go, but for our kind of sneak preview BGP, this is about all you have to know. Okay, onwards to TCP. So now we're going to up one more layer to layer 4. So first we have to remember why layer 3 was not enough to just be done. So why couldn't we stop at layer 3 and say, all done, internet's good to go? The reason was because of reliability. So reliability is the property where if I send a packet, it should be received by the other person correctly. Right? I want the other person to receive my packet. And if the packet has been changed, so either maybe the network has an error, so maybe the wire is buggy or the radio waves got tampered with or something, then the packet could get corrupted, or maybe an attacker has changed the packet. If that happens, I don't want this packet to be received because it's no longer what I intended to send. It's been corrupted. Now, to prevent against random errors, so these are kind of like errors of nature. So like the radio wave didn't send all the way, or the wire was bent or something, I don't know. But if there's a random error, IP packets do usually include something called the checksum. And the checksum is, it's not a cryptographic function, it's just an unkeyed function that protects against random errors. So almost kind of like a hash where you just kind of provide a fingerprint of the message so that it hasn't been tampered with, but there is no key, so it's not a cryptographic protocol. So if the attacker wants to modify the packet and they correctly modify the checksum, it will look correct even though it's been tampered with. So it kind of sort of protects against random errors because of the checksum, but it doesn't protect against intentional tampering because there's no cryptography. So that's IP. It kind of sort of defends against errors, but not really, right? So all we get is a checksum. There's also a bigger problem, which is not only do I not guarantee that packets are received correctly, I have no idea if a packet has been delivered at all, because IP is called what's called best effort delivery service. So it's kind of like, try your best. If it doesn't work, oh well, who cares? That also means that if a packet is lost, so it gets dropped, maybe at some point, some local area network just shuts down or forgets to send it, or I don't know, the packet has been stuck in a loop and it never reaches the destination or something, the packet could just not get there and nobody cares because it's best effort. The packet could be corrupted and maybe no one notices, so that could also happen. It could be tampered with, the packet could be delivered out of order, so this is a problem, right? If I send 2 packets, there's no guarantee who gets there first. So these are all problems with IP. It's unreliable, it's best effort. It's kind of like, I'll try to send, sometimes I succeed, sometimes I don't, and you just have to deal with that. So now it's kind of our job to create another layer or another level to ensure that connections are reliable, because this is kind of terrible. If I send a message to someone, I would like them to receive it. I would also like them to receive it correctly, right? And IP is not enough for that. So now we have to design an extra layer to ensure that. Okay, so here's how we'll design it. I guess there was no animation here. Oops. But there were 3 main problems with IP that we just talked about. So one of them, I think we only kind of touched on, but basically IP packets are limited in size. So an IP packet is only so big. So if I want to send a longer message, not only do I have to use IP, but I also have to manually split the message up, which is kind of annoying, right? Like if I'm sending a message, or if I'm writing code for a website and I have to send a message, I don't want to have to worry about manually splitting up that message into small chunks and then sending it. Or if I receive a message in a bunch of different small chunks, I have to figure out how to reassemble it. That's kind of a gigantic headache, and I don't want to deal with that. So TCP is like, okay, I'll deal with that for you. So when you send a packet in TCP, you can actually send as long of a message as you want in TCP, and TCP will automatically split it up into small IP packets for you. So that's great. And if you're using TCP and you receive a message, it will also automatically reassemble the packets for you. So you, as the web programmer or the network programmer, don't actually have to worry about splitting a long message because TCP will do it for you. So that's great. Another problem we talked about is packets can arrive out of order. That's a problem. So what TCP will do is it will kind of do the natural solution, which is I'll number all my packets. And that way, if I receive a packet that's out of order, I can just rearrange it into the correct order. So one way to think of this is we've been talking about how the internet's kind of like a postal system. So maybe I have 2 packages and they have to be opened in a certain order. I don't know why that would happen, but okay. So maybe I have 2 packages and I want to send them to someone, right? And they have to be opened in a certain order, or I want to identify that this one was the first one and this one's the second delivery. So sure. And normally I can do this, I can just stick a number on the packages, right? So before I send the box out, I'll just tape the number 1 on the first one and the number 2 on the second one. So this way, no matter which one shows up first, the recipient will know, oh, this box is the first one and this box is the second one. So that's basically what TCP does, is it just tapes a number on every package so that when the recipient receives a bunch of different packets, it can see all the numbers and then put them back in the right order. Okay. So that's a kind of a useless analogy, but that's one way you can think of it, is I'm just basically taping numbers on packages. The third problem is packages can be dropped, or packets can be dropped. So maybe a packet doesn't show up, and I have to know, if I'm the sender, I would like to know that the packet has been dropped so I can send it again. So I need to know if the packet succeeded or whether it failed. So the way we do this in TCP is, if I send a package to someone and they receive the packet, not only should they receive it, they should also send me like a thank you note or like a postcard saying, I got the packet, thanks. And that lets me know that, yes, I for sure received the packet and I'm safe and I do not have to resend it. But if the thank you card never comes, or the postal, like the postcard or the recipient notice or the receipt has never arrived, that lets me know, maybe they did not get the packet because I never received an acknowledgement that the packet arrived. So let me just resend it so that I'm sure that they got it. And I will basically send this packet over and over and over again until the thank you note or the receipt or the acknowledgement came through. Someone asked a very good question, which is, what if the acknowledgement packet or the thank you note or whatever doesn't come back to me? Because that's also a packet and that could also be dropped. So we'll see how that's solved in like 2 slides, but that's a very good question. But yeah, the general idea is when I send a message, always expect a response telling me that it has been received. So these are basically all the design goals that you're going to get out of TCP, and they basically solve all the problems that IP had. So now we can actually see it in action. So here's TCP. It provides what's known as a byte stream abstraction. That's kind of, again, a lot of words. But basically, a byte stream abstraction is what we talked about earlier, where we said, well, the problem here is I don't want to have to split messages up into packets. I would like to just be able to send a gigantic message, and TCP will break it up and reassemble it for me. So that's what a byte stream abstraction is. So at all the lower layers, I had to think in terms of packets. My mindset was always, these are small packets that are flying across the internet one at a time. That was my lower layer perspective. But now that we're moving into higher layers, because of TCP, there's something called a byte stream abstraction. And what this means is, instead of thinking of messages as small packets of a certain size, I can think of messages being sent and received as one long stream of packets. So I no longer have to think in terms of small packets. I can think in terms of there's just one giant stream of things going in, and there's one giant stream of things coming out. And that's all I have to think of. I don't know if anyone remembers what ticker tape is, but back in the old day where stocks were being, I guess, like people needed to know like the latest stock prices or whatever, there would kind of be this tape machine or a ticker tape machine, and all it would do was just spit out stock numbers all day in like this giant long string of paper. And so you can think of, I guess, TCP as kind of like a ticker tape machine, because you never have to think of, oh, this message is too long for a packet or anything. All you see is just this giant stream of stock prices coming in on this like endlessly long roll of paper. And you can just keep pulling, and there'll be more information coming in. So that's kind of what the byte stream is. It's ticker tape. I don't know why all my analogies have been getting like older and older. Like we went for postal systems, like ticker tape, and like tomorrow we'll be talking about like, I don't know, like the telegraph or something, but that's okay. Yeah, punch cards, I don't know. Okay. But anyway, so TCP, again, is just kind of one long tape of information coming in at you, and TCP will automatically break the streams up for you. Sometimes you see the term segments, which is just another word for the packets that TCP splits your message into. But none of this you have to worry about. So if you're programming at a higher layer than TCP, you can think in terms of the stream of bytes. You don't have to think in terms of segments, because TCP will translate that for you. There's also ordering, so we talked about this already. TCP will have sequence numbers inside every packet or every segment, and this way the destination can reassemble the stream and order it for you. There's also reliability. So we talked about this also. If you receive a packet, you always send an acknowledgement to let the other person know that the destination, that they've received the packet. So I don't think they call it thank you cards in TCP, but they do call them acknowledgements. So that's what provides reliability. Okay, and then we said this also, but if you don't receive the ACK, so if I send a message and an ACK never comes back, so I have no idea whether they received it or not, I'll usually just send it again and again and again and again until I receive the ACK. So that is basically the way to provide reliability. Okay, that's basically it for, I think, the high level design of TCP. So now we can start digging in. TCP has one extra feature that we haven't quite talked about yet, and it's called ports. So before we talk about ports, here's yet another analogy for you. I think this one's also kind of outdated, but back in the day, there was something called pen pals, which is you find some person from some other random country and you just write letters back and forth. I don't know why they did this, but I guess it was entertaining for some people. So let's say Alice and Bob are pen pals for whatever reason. Okay. And then Alice has a roommate. So Alice's roommate is Carol. They live together. And Carol is also pen pals with Bob. So both of them would like to send messages to Bob. And Bob would like to send replies to both Alice and Carol, right? But here's the problem, which is if Alice and Carol both send a message to Bob, they are in the same apartment building or the same house. So when they send a message to Bob, they're using the same sender address or the same IP address. And when Bob sends a reply, the reply comes back to the same IP address, regardless of if it's for Alice or if it's for Carol, right? Because they live in the same place. So obviously all the replies come back to the same place. That's a problem. So how do we tell what letters are for Alice or what letters are for, I shouldn't say Bob, I should say Carol. So how do we tell, who's who? Is this for Alice's room or is this for Carol's room? So this is what ports are for. You can think of them as like room numbers, right? So maybe a building or a house or an apartment could have different people living inside of it. There could be different rooms inside of it. And so not only do I have to address the letter to a certain house or a certain address, I also have to address this letter to the correct room so that it reaches the correct recipient. So if you're in a private home, the port number doesn't really have any meaning to it. So you can just arbitrarily say, Alice is room 1 and Carol is room 2. Right? It doesn't really matter what those numbers are. As long as Alice and Carol, when they send a message to Bob, they include the room number so that when Bob replies, Bob can say, this is for room 1, this is for room 2. And then Alice and Carol can separate out their letters. Right? So in private homes, those numbers could be basically anything, and it doesn't really matter what they are. As long as Alice, Bob, and Carol agree on what the numbers are, then it's all good. But if you're in a public office like Corey Hall, which is the EECS department at Berkeley, the port numbers, the room numbers kind of have to be constant, right? You can't just randomly change a room number because then you no longer know where anything is, right? That would be kind of wacky if you showed up to Corey Hall for class and all of a sudden the numbers have been shuffled. That would not be great. So if you're in Corey Hall or like some public server, the port numbers should be constant and everyone should know where they are. So if I tell you, let's have a meeting tomorrow in Corey 212, everyone shows up at the same place. So everyone should know port numbers in public places like Corey Hall. But if you're in an apartment like Alice and Carol's apartment, then the room numbers can kind of be whatever. So those are ports. That's something that is added on top of TCP, or TCP adds it on top of lower layer protocols. And what ports are for is if you have a computer or a server and the server is running lots of different applications, the port lets us distinguish different applications on one computer. So maybe my computer today is running Zoom, it's running Firefox, it's running Slack, it's running, I don't know, some other applications, right? And I have to have a way to distinguish which packets are meant for which application. So maybe Zoom and Firefox and Slack are all sending out IP packets or TCP packets, but when the packets come back, they're all going to come back to the same IP address because my computer has one IP address. But my computer has to have a way of distinguishing if a packet comes in, is this a packet for Slack? Is it a packet for Zoom? Like, who is this packet for? I have to figure that out. So that's what ports are for. So port is a number that tells us, well, this is a packet for Zoom and this is a packet for Slack and so on. Again, on private computers, these can basically be whatever, right? So none of you care whether my computer currently is using port number 50 or 51 for Zoom. It doesn't matter. As long as Zoom knows that I'm using this port number, they can send the replies to the same port number and we're good. So it doesn't matter for most people what port numbers I'm using because I'm using a private computer. But if we're using a public server like Google, then the port number should probably be well known and constant. So maybe Google has this big server and this Google server is giving us search and images and maps and mail and all those different things. Then Google should probably tell everyone, if you want to search, use port 100. If you want to look for an image, use port 200. If you want to look at a map, use port 300 and so on. So a server like Google that's public should tell everyone these are constant ports. And if you want to contact Google, you know exactly which ports to contact. So this is kind of the analogy from before. Now remember, again, TCP is built on top of IP, so ports do not replace IP addresses. We're not swapping out IP addresses or anything. We're adding them in addition to IP addresses. So the IP header from the lower layer is still there. We still need to figure out which IP address is being sent to for the routing, right, the BGP routing, or to figure out which computer this is for. But once it reaches that computer and that computer takes off this IP header because it's done being used, it's gotten to the right computer, it needs to see this TCP header and figure out, oh, this is a message for port 80. So I'll send this packet to port 80 for processing. So that's ports. Okay, now going back to sequence numbers, I guess this lecture kind of jumps back and forth, but that's okay. So we talked about sequence numbers for keeping things in order. And to do so, we need two sets of sequence numbers. Now, the reason why we need two sets is because TCP is kind of bi-directional. So it's not like it's only me sending packets to you. or it's not like only the other person is sending packets to me. We're going to be actively talking to each other, right? So if Alice and Carol are pen pals, Alice and Bob are pen pals, they're going to be sending packets back and forth. So it's not like it's only one person sending, they're both sending. So because there are two people sending and receiving, we need two sets of sequence numbers. So there's one numbering set for all the packets from Alice and Bob, from the client to the server. There's another set of sequence numbers for all the messages from the server to the client. So you have to keep track of two numbers, and the two numbers keep track of different streams, right? So there's one stream that this client is inputting and the server is pulling out as ticker tape. There's another stream that the server is putting in as a stream, and then the client is pulling out as ticker tape. So there's two streams going two ways. So there's two numbers that are kind of being incremented. And before you start, you have to agree on initial sequence numbers. So we have to figure out what's the first sequence number that either side is using. Now, you might think it might be enough to use 0, but for security reasons, as we'll see like in a couple of slides, the initial sequence numbers are actually different for every connection, and they're random. So here's an example. So this is a message from the client to the server, so that's hello server. And this is numbers starting at 50. So we go, the H is 50, the E is 51, the L is 52, and so on, right? So this stream, every byte is numbered, and there could be more messages after this, and they would start at 62 and keep going up. And this stream is all the stuff being input by the client, sent over TCP across the internet, and received by the server. So this is one stream. Another stream is going the other way. So this stream says hello client is starting at 25, so it's a different number. This stream is consisting of all the bytes that the server is inputting, going through TCP and the internet, and coming out on the other side for the client to receive. So notice there are two sequences of numbers that we have to keep track of. Okay. So how do we agree on like the numbers 50 and 25 here, right? They have to both agree that the client is going to start at 50 and the server is going to start at 25. So that the way this works is called a three-way handshake. So there's three messages to be sent to confirm this. So the first message is called syn or synchronize. So the client says, hi server, here's my initial sequence number, it's X. The client says, any message that I send for you, I'm going to number it starting at X. So the first message I send you is X, the next one's X plus 1, the next one's 2, the next one's 3, and so on. And then the server says, okay, let's connect. So I will give you my sequence number as well. So my sequence number is Y, and I'll give you a packet. This one's called synac. So we'll see more of that later, but the name for it. And the final packet is called ACK. And this packet just says, I have confirmed that I have received your sequence number. And now we both agree that we will start from X and start from Y and increment from there. And you'll see here that there are sequence numbers, so we'll talk about these soon, but you can see that every byte is already being numbered with sequence numbers. So even while we're agreeing on sequence numbers here, we're already starting to keep track of sequence numbers. It's kind of funky, but that's how it works. So the three-way handshake is always syn, synac, and then ACK. And the purpose here is so that both sides agree on the sequence numbers to start with. So the client sends their sequence number, the server responds with their sequence number, Y, and then the client acknowledges that they've both been received. Okay. So that's the handshake. And then once they're done, now they can start sending data back and forth. Okay, so we'll see a bit more of that in just a minute, I think, but let's talk a bit about how you send and receive data. So for every connection, there's generally like a TCP handler, and usually the operating system does this for you. And the handler or the operating system will keep track of every different TCP connection. So every computer can have different TCP connections running at the same time. Again, I can run Zoom, Firefox, Slack, etc. And the way I identify a single connection is by 5 different unique values. So they are these 5 values. So for every connection, there are these 5 values. And if any of them are different, then you have a different connection. So the source and destination IPs, the source and destination ports, and the protocol. So this uniquely identifies a single application on my computer talking to a single application on a single server. That's a single connection. If I have a different connection on my computer talking to the same connection on the same application on the server, that's a different connection. Or if the same application on my computer is talking to a different server application, that's a different connection. So every unique pair of like sender and recipient is one connection. And that's why there are these 5 values. And I think the protocol is just always TCP or TCP over IP or something, but it's not that important. Okay, and then because the TCP handler or the operating system is doing all this for us, the application, right, can only has to see the stream of information showing up or being sent. Okay. And it's the TCP handler or the operating system's job to make sure that the packets are coming in order and being received out of order, or being received in order, and when they're being sent, that we're stamping numbers on every single packet so that they're sent in order or received in order. So all this ordering stuff, the TCP handler will do it for us. Okay. So now we can kind of see how sending and receiving works. We've talked about this already. Every byte has a sequence number, and the sequence number is different in the two byte streams, right? So the first byte is x plus 1, and then it goes x plus 2, x plus 3, x plus 4, and so on, and it counts up. And the sequence number in a packet, so you can think a packet has a lot of data, right? So maybe this packet has 100 bytes inside. Well, I don't want to label all 100 bytes because that's a waste of space. So the way I label a packet with lots of different bytes is I label it with the first byte of the data. And I assume the data inside is all consecutive. So if I have a packet with 100 bytes and the sequence number is 73, then what we're saying is these are bytes 73, 74, 75, 76, all the way up to 173. And that's the sequence number. And this number is from the sender's set of numbers. Remember, there's a set of numbers for sender to receive, from server to client. There's another set from client to server, right? So which set of numbers am I using here? I'm addressing these relative to the sender's set of sequence numbers because I'm the one sending them. So it's from my sender's numbering sequence. The packet also has something called an ACK number. So these are numbers inside the packet. Right? So every packet that gets sent or received has a sequence number and an ACK number inside the packet. And that's built into TCP. So the sequence number tells us which number of bytes are being sent. The ACK number is a number that tells us which bytes am I acknowledging. So I can actually acknowledge the receipt of a byte while I'm sending more. So this kind of saves us some time, right? It would be very inefficient if I sent a message, I wait for the acknowledgement, and then once I get the acknowledgement, I send another message, I wait for the acknowledgement, and then I get the acknowledgement back. That would be simple, but very time consuming because I have to wait for an acknowledgement every single time. So instead, what we do is we actually are going to acknowledge packets while we're sending packets. So while I send you data, I will also add a number that says everything up to this number, I have actually acknowledged. So I've received everything up to this number. So that's the ACK number inside of the packet. Notice that this number is from the other set of sequence numbers because I am acknowledging messages from the recipient or from the other person. So the ACK number comes from the receiver's set of sequence numbers. That's kind of a weird thing to wrap your head around, but hopefully it diagrams will help. So just remember there are two sequence numbers being sent in every single TCP connection. The sequence number tells us what bytes are being sent. The ACK number tells us what bytes have been received and have been processed. Okay, so here's a diagram. I hope this clears things up, but this comes after the handshake is over. So the handshake used up a couple of bytes, which is why the sequence number actually starts at the initial number plus 1, and the ACK number starts at the initial number plus 1. So here, the client's sequence number starts at X, and the server sequence number starts at Y. So the reason why this starts at X plus 1 is because we're saying this packet that I'm about to send you, the first byte in this packet is index X plus 1, and then we're going to tick up from there. And the acknowledgement number says, I have acknowledged every single byte up to, but not including, I think, Y plus 1. So the next byte you should send me is Y plus 1. Okay, and Y is relative to the server because those are bytes being sent by the server. So here's some data along with the packet, and it's of length A. Okay, now it's the server's turn to send. So the server says, okay, I have now started to send you messages. My message starts at Y plus 1. So notice how these swap, right? In the client's perspective, the other person is the server, so it's acknowledging messages from the server. From the server's perspective, it's sending messages as the server. So the sequence number should be the server sequence number, which is y+1 because that's the first byte of whatever the server is sending. And the ACK number says, I have received all of your data up until x plus 1 plus a. So the next thing you should send me is x plus 1 plus a. And the way we got this is, well, the last packet started at x plus 1. It had a bytes of data. So the next byte that has not been received yet is x plus 1 plus a. So we're kind of ticking forward as we go. And this continues, and you can trace it yourself if you'd like. But right, so now the next sequence number, because I've sent x plus 1 so far, and I've also sent a, the next thing that's coming should be x plus 1 plus a. Right? I can also think of this as, well, the server told me it's accepted everything up till x plus 1 plus a. So the next thing that should come is x plus 1 plus a. So that's the next sequence number. And the ACK number here says I received everything up to y plus 1 plus b. And I know that I've received that because the last one had y plus 1. It started at y plus 1. It went all the way up to y plus 1 plus b bytes. So I've acknowledged everything up until there. And then I also sent some data. And this goes back and forth and back and forth. And you're welcome to trace it yourself. I think discussion will also trace it a bit more. But it is a little bit tedious, to be fair. I don't think you have to worry too much about it. But all you have to know here is that we are numbering every byte of data that's being sent. So no matter which direction we're going, there's a number. And when we receive something, we're also sending an acknowledgement number to say, I have received every byte until this one. So the next time you give me data, start here and give me everything from here on. So that's sequence and acknowledgement numbers. Any questions? It definitely kind of like takes a bit of staring at, so it's understandable. Okay. So let's talk really quickly about retransmission. Someone asked this a long time ago. It was a very good question, but we've already talked about what happens if a packet is dropped. So if the packet is dropped, the ACK will never come, because if I don't receive the packet, the ACK will not come. If the ACK doesn't come, I just repeatedly send it again until I get the ACK. Right? And in the numbering system, what happens is the ACK number will be too low. Right? So the ACK number will be lower because I haven't received some of the bytes. So I'll resend all the bytes starting at the most recent ACK. And that's how it resends things. Now, someone asked this one, which is, what if I receive a packet? What if the packet has been received, but the acknowledgement got dropped? This is kind of weird. But what happens is, if the ACK is dropped, the sender thinks that the packet has not been received because it never received an ACK. So the sender will just resend the packet anyway because it didn't get an ACK. The recipient will receive duplicate data, right? It'll be like, I already got this. Okay, sure, I'll take it again. And I'll send an ACK again because it just received the same data. And I'll say, yeah, I got this. Trust me, I got it for sure, you're good, right? And then it'll send the ACK. And now the sender will receive the ACK, and now the sender knows that it's been received. So this process could also repeat. So if the ACK keeps getting dropped, the sender will continue to resend over and over and over again. The recipient will keep receiving duplicate data over and over again and keep sending out ACKs over and over again to say, dude, seriously, I got it, I got it, I got it, I got it. And then eventually one of those ACKs will reach the sender, and the sender will be like, oh, okay, you got it, we're done. And that's how you handle ACK being dropped. Okay, and I think usually TCP will slow down if too many packets are dropped. So usually if lots of packets are dropped, that usually means the network is congested or it's too crowded. So things are getting dropped because there's not enough space to send everything. So usually TCP will slow down, but you don't have to worry too much about that. Okay, so that's how you run things within TCP. Now we have to ask about, how do you end a TCP connection, right? What happens when you're done? So there's two ways to end. So there's one way of ending, which is like, let's play nice and end. So this is a legitimate standard finish. The way this works is, when you're done, you send a packet with a finish flag, and we'll talk about flag, I guess, in the next slide. But we'll send a packet that's labeled finish, that says done. And that packet has to be acknowledged to say, I received your finish packet. This finish packet says, I am done sending, so you will never receive another packet from me in this connection. But if you like, you can keep sending me packets and I'll continue to receive them. And once both sides have finished, that's the end of the connection, right? Because if I'm finished, I'm no longer sending packets. If the other side is finished, they are also no longer sending packets. Then there's no more packets and the connection is over. So this is kind of a nice two-way end. So both sides have agreed to end because I agreed to no longer send packets. The other side acknowledges that they have received this finish, and the other side will also tell me that they're done, and I will also acknowledge that they're done. So this is a two-way nice finish. But things are not always nice. Something could go horribly wrong. There could be like an emergency, right? Maybe the server crashed or the internet connection is about to break, right? Or an attacker is here and I have to quit really quickly. So this is for aborting, emergency aborting, and this is called reset, right? So if I send a reset packet, that basically means I'm done, something has gone wrong, and I am no longer sending, and I'm no longer receiving. So I'm leaving, goodbye, forever. And reset packets are not acknowledged because I'm not sending and I'm not receiving. So what do you care, right? You're never going to be able to reach me again in this connection. So there's no acknowledgement. This is kind of like an emergency stop. So you push the big red button and send the reset, and this connection is over. Without any acknowledgement, without any agreement from the other side, it's over. Okay. I guess flags are all the way back here for whatever reason, but TCP has a bunch of different flags. So inside a packet, we've said the packet has data. The packet has sequence numbers and acknowledgement numbers for sending and receiving data. It also has these things called flags. So these are labels that are either on or off. And each TCP packet has all these flags, and you can set as many of them on or off as you want. So the first flag is called ACK. This flag is basically always on, and this flag basically says, look at the ACK number because I am acknowledging the receipt of all the packets up to the ACK number, or all the bytes up to the ACK number. Now, as we saw, usually when you go back and forth, almost every packet has something to acknowledge. So the ACK flag is usually always set to be on, but occasionally maybe I'm sending some data without having received any data, in which case the ACK flag would be off. There's also one called the SYN flag. This is the one for when we connect. So remember how way back in the TCP handshake, there was the SYN flag and then the SYN-ACK flag, or the SYN message and the SYN-ACK message. The reason why they were called SYN and SYN-ACK is because the SYN message has the SYN flag on, and that tells us that we are beginning a connection and we're establishing a sequence number. So the first message is called SYN because we're establishing the initial sequence number. The second message is called SYN-ACK because I'm establishing the second sequence number and also acknowledging the first sequence number. So we're SYN and we're doing ACK. And the third message is called ACK because the sequence numbers are done, so there's no more SYN, but there is an ACK because I have to acknowledge that the second sequence number has been received. So that's the SYN and the ACK packets, or the flags. There's the FIN packet, which we saw was one way to end the connection. And we do need to acknowledge the FIN because that's the nice way to end. And the reset flag is the one for emergency stops. So those are the 4 flags that we care about. There are some other ones, but these are the main ones. Okay. Now we can finally see, I realize that we're running a bit long. Sorry about no break, but yeah. So here's the packet. We've seen a lot of this already, right? We saw the source port. We saw the destination port. Those are for picking an application on the machine. We saw the sequence number, which is for labeling the bytes that are being sent. We saw the acknowledgement number, which is the label. I have received all of your bytes up to here. Here are the flags. So if you want to set SYN, ACK, FIN, reset, they'll all show up here in these flags. There's a checksum to prevent against random tampering, but it's not enough to prevent against malicious tampering. And then there's some other stuff that we don't care about. And then at the end, there's data. So that's a TCP packet or a segment. And this is the header, and then the data is down here. So here you can see all of it in all of its glory, I guess. Okay. I think that's basically it for the protocol. I think we're almost around time, so I'm just going to blaze through attacks, and then we can all relax and take a break after this. But the main attacks in TCP basically come from the fact that even though we have reliable data sending now, we still have not protected the data that we're sending. So all of this is great, but notice that in all of this discussion, we did not use a single cryptographic protocol. We didn't encrypt, we never used MAX, we never signed, we never hashed, no cryptographic protocols. So all the messages are still being sent in pure, unencrypted, unmacked, plain text. And that's where most of the attacks come from. Because everything is in plain text, the attacker can and will try to modify or delete packets that are being sent. So this is called TCP hijacking. And basically what we're doing is we're going to take a connection that already exists and try to change the data that's happening inside. And that's TCP hijacking. The different things you can do while you're hijacking a connection are you can inject data. So I add extra information that used to not be there, but I'm putting it inside the connection. And notice that if I'm doing this, I have to know the sequence numbers, right? Because I need to provide a packet with the correct sequence number in order for it to be accepted. If I'm the attacker and I put in some data with the wrong sequence number or no sequence number at all, the recipient will be like, wait a minute, I don't understand where this is or what order this should be received in. So it's going to reject the packet. So when you're injecting data as an attacker, you need to know the correct sequence numbers. Now, we can start thinking about all those attackers from before and think about who can do this and who cannot do this. Well, if you're a man in the middle or if you're on path, you can read packets. If I can read packets, I can see the sequence numbers because they're not encrypted or anything. So I'm good to go. All I have to do is look at the sequence number, and now I can inject my own packets with my own sequence numbers. But what if you're off path? What if you can't read packets? Then you have to guess the sequence number because you don't know. You haven't seen it before. You haven't read any messages. So if you're off path, you have to guess 32-bit sequence numbers. This can be kind of hard, and we usually call it blind injection or blind hijacking because you can't see packets. So you're flying blind, and you have to guess. And that is usually considered a bit more difficult. So TCP against off-path attackers, well, they have to guess, so it's kind of hard. TCP against on-path attackers, you're a host. There's no security because they can just check the sequence number and inject. Man in the middle, no security because they can just check the sequence number and inject. For on-path attackers, there is kind of one slight caveat, which is that they do have to beat the legitimate answer. So if there are two responses coming at the same time and they have the same sequence number, one of them is from the attacker, one of them is from the server, the attacker's message has to get there first because, again, the client usually accepts the first packet that shows up. So if you're on path, you generally do have to race. If you're a man in the middle, you don't have to race because you can just delete the server's response and replace it with your own, or take the server's response and then change it. So man in the middle, they can just change. On path, they have to race. Off path, they have to guess and race. The second attack that's kind of related is instead of injecting data, we want to be evil by cutting off this connection. So let's send a reset packet to just stop this connection immediately. So I'm trying to mess with their connection by just ending it. Again, the requirements are basically the same. The reset packet still has to have the right sequence number for it to be accepted. So I still have to figure out the sequence number for injection. If you're man in the middle, that's super easy. I just look at the packet. If you're on path, that's super easy. I just look at a packet. If you're off path, you have to guess. So it's a little bit harder. So that's reset injection. Sometimes we'll see this in censorship. I think we may have a lecture toward the end about censorship, but basically reset injection comes in play when you're dealing with censorship because if you're trying to censor someone's connection, right? If someone makes access to a site you're trying to censor, you just reply with a reset injection and that stops the connection immediately. So you can use this for censorship. Okay, any questions about any of the attacks? They basically all come down to the same thing, which is you have to guess the sequence number, and it just depends on how hard or easy that is. Okay. So here's an example of injection. So here comes a piece of data, right? The server receives the data. Now here comes the attacker. The attacker sends evil data, and notice that the evil data has to have the right sequence number before, because the client is telling the server, I got all your messages up until y+1. You should now give me messages starting at y+1 and going onwards. So the attacker needs to comply with that and say, yes, okay, here are your messages from y+1, and here's the evil data. And if this works, then it will be received by the client. And if it gets there first, then maybe the server sends some real data, but it's too late because the client has already accepted this malicious data. Notice that this is spoofing kind of, right? Because, not kind of, it is spoofing because this red arrow here, the attacker is pretending that this is from the server. So if you look at the IP packet here, it will say from server. So they're spoofing who this is from. So this is a spoofed packet. And if the spoofed packet shows up first to the client will accept that. So that's injecting data. So again, this is spoofing because we're trying to fake the source IP address. So we're saying this is from server, even though it's from the attacker. And we have to make sure that we're using an autonomous system that doesn't prevent spoofing. Okay, I think this is a slightly different attack. So this is one where we're trying to start a connection as if it came from someone else. So this is called TCP spoofing. In this case, we are not trying to inject into an existing connection. We're going to try to start a brand new connection from somebody else. And so let's take a look at the diagram. Again, you'll notice a pattern here, which is that if you can read sequence numbers as a man in the middle or an on-path attacker, this is super easy. If you're off-path, you have to guess, which is hard. So again, kind of the same pattern as before. And again, kind of the same as before, there is a race condition if you're on path because you have to get there first. So this one, I think a diagram is the most helpful, but here we go. So remember, our goal here is we're an attacker trying to create a connection, even though the connection doesn't exist. So here's a SYN packet from the attacker. We're pretending that it's from the client because we're spoofing. So we're trying to create a connection when one doesn't exist. So we're going to say, this is a message from the client to the server, and the client is trying to connect. And this is all lying, right? So the client is not trying to connect, but the attacker is going to pretend that the client is trying to connect. Now the server is going to send a SYNAC. And because the server thinks the client is trying to connect, the SYNAC is not going to go to the attacker. It's going to go to the client because this is a spoofed packet. It says from client to server. So the server will see this and be like, oh, okay, then I'll reply to the client. So this SYNAC, which contains the server sequence number right here, the Y, it goes to the client and the attacker might not be able to see it. So if the attacker is man in the middle or on path, they can see this. If they're off path, they can't see this. Now the attacker is now going to send the final part of the handshake, which is the ACK. And the ACK requires both sequence numbers. So the X is easy because the attacker chose X. The Y might be hard because it was only sent to the client. So if you're man in the middle, it's easy. If you're on path, it's easy. If you're off path, this Y is hard to guess. And once you finish with the ACK, you can start sending a bunch of default data. So you've spoofed a connection. You've created a fake connection from the client to the server, even though this connection didn't exist. And usually what happens here is this client was not expecting a connection, but it received a SYNAC. So if you're just sitting there and someone randomly SYNACs you, you're like, what? Why did I get a SYNAC? That's weird. So usually the client will reset here and say, I think you messed up. Here's a reset packet because I'm not trying to connect with you. I don't really want to talk with you. So let's just reset and call it quits. So usually the client will eventually reset to stop this connection because it's so weird. But before this reset shows up, the attacker could inject a lot of evil data before the reset shows up. So maybe the attacker can send some data to the server like, hi, I'm a client and I would like to transfer $100 to attacker or something. Okay, so that's TCP spoofing. It's kind of weird, but basically the main takeaway is that you are trying to impersonate, as the attacker, trying to impersonate a TCP handshake from the client. Okay. And again, if you're a man in the middle, you can always just drop the reset and then you can inject as much as you want. So if you're on path, you generally have to race against the reset. If you're man in the middle, you can just drop. And then if you're off path, not only do you have to race, but you also have to guess the sequence numbers. Okay. Let's see, I think we talked about this already, right? There's no crypto. We never ever talked about any MAC or encryption or anything like that today. So that has not been talked about today, but we will talk about all of that tomorrow. So stay tuned for that. Remember way back we asked, why did TCP use random sequence numbers? Why didn't we just start at 0 every time or use a timestamp or something? Now you know why, so we've put all the pieces together. Now we see that the reason why we're using random sequence numbers is because we want off-path attackers to have a very hard time guessing them. So now we know why we're using random sequence numbers. If we use bad randomness, like a poor PRNG, or we just see the timestamp or whatever, that could be terrible because now the off-path attacker has a very good chance at guessing sequence numbers. And that lets not only man in the middle and on-path, but also off-path attackers mess with TCP. So that could be a problem. Oops, I guess that's it. Okay, we're really short on time, but I promise we're almost done. The last and very short topic is UDP. So at the transport layer, we now have reliability. But here's a very funny question that you might ask, which is, what if I don't want reliability? Is there ever a case where I don't want reliability? Well, there is, and those cases are solved by something called UDP. So UDP is just the message sent in a single packet. It is limited in size, so it's just like an IP packet. And it's the application's job. So now it's not like TCP where you can just send a byte stream. The application has to manually break their data into small datagrams to be sent and received. And the other person has to manually reassemble them. So it's not like TCP because there's no byte stream. You have to manually split messages and send them one at a time. There's no reliability, no sequence numbers. There's no ordering, no sequence numbers, no ACKs. There are ports, so you can still talk to other applications. So everything from layer 4 and above is always has guaranteed application separation. So there are ports, but there's no reliability, no sequence numbers, no ACKs. It's still best effort. So basically, if you think about it, UDP is literally just IP plus ports. Right? We're still limited by size, no reliability, no ordering. I just added ports. Right? So it's just the transport. It's kind of like the bare bones transport layer that just adds ports for applications. Now, this seems horrible. Why would anyone ever use this? The main reason is because it's fast. UDP is super fast. Why? Because there's no three-way handshake, and messages are best effort. So you can just flood all the messages at once, right? You don't have to wait for ACKs to come back, or if something fails, you don't have to resend. You can just blow messages toward the recipient as fast as you possibly want, right? There's no, right? Whereas like in TCP, if a message doesn't show up, you have to sit there and wait and resend until it shows up. But in UDP, you'd be like, oh, I dropped one, who cares? Go, go, go. And just keep sending as many messages as you want. Now, why would you ever want to use this? Well, if speed matters and dropping a couple packets doesn't matter to you, then UDP is the way to go. So for example, video streaming, right? If you're streaming Netflix and there's a single byte that keeps getting dropped, do you want the entire video to stop while it waits for that single byte to show up? Or would you rather just get one frame of the video that's a little bit worse, but then immediately after it keeps going? You would much rather the video keep going, right? So that's where UDP is useful. Or maybe like a game, right? If a packet doesn't show up, you don't want the whole game to freeze up waiting for a single packet to show up. You want to just say, yeah, forget it, drop that packet. Let's just keep going as fast as we can. So video streaming, Zoom uses UDP, I bet, games, stuff like that. So if you're looking for speed and you don't care about a couple of packets getting dropped and you don't want to wait for the handshake and stuff, UDP is the way to go. Okay. Now, a couple of attacks. Someone said maybe Netflix uses TCP because the video is pre-recorded. Yeah, I guess, right? Because Netflix can stream ahead of time. But if you're live streaming, then yeah, UDP is the way to go. Okay, fair enough. I guess I'm showing that I've never used Netflix before because I watch videos on other legal methods. Okay, let's talk really quickly about attacks on UDP. So there are no sequence numbers. So again, you can inject as much data as you want. In fact, if you're an off-path attacker, you can even attack UDP because there are no sequence numbers and no ACKs, right? So I think this is basically the only slide for UDP because it has no security whatsoever. You can just inject whatever you like in UDP because there are no sequence numbers. Anybody can inject. So that's bad. And here's the packet. You'll notice it's extremely simple, much simpler than TCP because it's just the regular IP with the data, and I put a source and destination port on top. And that's it. That's UDP. And now we're finally at the end. I guess whoever said this lecture was going short completely lied because we spent the entire hour and a half on it. But let's just quickly talk about what we talked about today. So BGP is a protocol for routing packets. If we're on the internet and we want to get a packet to someone on a different local network, we have to hop across the internet until we find them. And the way to do that is to use autonomous systems. So every system broadcasts the list of shortest routes that it knows from its neighbors, and eventually you'll broadcast a successful route to the destination. And there are some attacks here, but we usually rely on higher layers to defend against them. Then we talked about TCP, which is how we reliably send packets. To start a connection, you do a three-way handshake, and the three-way handshake lets us agree on initial sequence numbers. Then in future packets, we use sequence numbers to ensure that messages are sent in order. That gives us reliability. It gives us messages showing up in order. And if we add ports, it gives us messages showing up to the correct application. There are a couple of attacks. So there's TCP hijacking, which is where you inject data or inject a reset injection, a reset packet. And if you are doing this as an off-path attacker, you have to guess sequence numbers. That could be hard. If you're spoofing TCP, you have to race the reset response from the real packet. If you are an on-path attacker, if you're off-path, you have to also guess the sequence number. So those are the attacks on TCP. Again, the general theme here is if your man in the middle is super easy. If it's on path, you have to race. If it's off path, you have to guess and also race. And then finally, we talked about UDP, which is what happens if I want to go fast and not send packets reliably, but just make sure that stuff gets there as fast as possible. That's UDP. It gives us no reliability, no ordering. There are ports, though, and it still has the same injection and spoofing attacks, but they're a lot easier because there are no more sequence numbers. And now we finally made it to the end, only 1 minute late. So any final questions? Sorry, this really went a lot longer than I thought. Okay, there's nothing else. I'll see you tomorrow, and tomorrow's all about crypto, using crypto to secure all this stuff. So stay tuned for that.